right? So let's look at some calculation examples of this. If I have 5 moles of sodium chloride dissolved in water, I want to know how many moles of Na plus ions are going to be formed in solution. Well, if I start with my 5 moles of sodium chloride, I know that for every 1 mole of sodium chloride I get 1 mole of Na plus, so I'd end up with 5 moles of Na plus. A pretty straightforward calculation, but keep in mind I'm using that mole to mole conversion between the formula and the ions. Alright, what if I had 6.75 moles of H2SO4 dissolved in water? How many moles of H plus ions am I going to have? Well, I've got 6.75 moles of H2SO4. My ratio is going to be 1 mole of H2SO4 to 2 moles of H plus. So I'd end up with 13.5 moles of H plus. So it's important that you recognize what ions are going to be formed and how many ions are going to be formed when these things break apart in solution. Alright, if I have 13.75 grams of C12H22O11 dissolved in 15.5 milliliters of water, how many moles of C12H22O11 are in solution? This is where I've started with the mass now, not moles. Remember, I can't just break it up into ions from the grams. I have to start with the moles. So if I have grams, what do I do to get it to moles? Well, I'm going to use my molar mass. So I'm going to start with the 13.75 grams. And 1 mole of that C12H22O11 is 342.30 grams of C12H22O11. Multiply those out, I get 4.017 times 10 to the negative 2 moles of C12H22O11. So if I'm starting with moles and dissolving it, I can talk about those moles. If I'm starting with grams, I got to get it to moles first. Now from this, how many moles of H plus are in solution? Alright, well, it's a trick question. This is a non-electrolyte, so we wouldn't have any. No ions are going to be formed. But we'd still have 4.017 times 10 to the negative 2 moles of that C12H22O11 dissolved in solution. Alright, let's look at another example of this calculation. If I take 7.25 grams of magnesium chloride and dissolve it in 127.5 milliliters of water, how many moles of magnesium chloride am I going to have in solution? Remember, I need to get it to moles based upon the molar mass. So I'm going to start with the 7.25 grams, use the molar mass, and I get 7.61 times 10 to the negative 2 moles of MgCl2. Now I could ask how many moles of Mg plus are in solution then. Well, that's just a simple conversion. I start with that many moles of the MgCl2, set up my mole to mole ratio from the formula, and I get 7.61 times 10 to the negative 2 moles of Mg2 plus. Because for every 1 mole of MgCl2 that dissolves, I get 1 mole of Mg2 plus. What if I wanted to look at how many moles of Cl minus are in solution? Well, I'd still take that same number of moles of MgCl2, I'd just have a different ratio. Instead of going to Mg2 plus, I'd go to Cl minus. I'd get 1.52 times 10 to the negative 1 moles of Cl minus. Now keep in mind, we're talking about moles of these things dissolving. What's actually happening and what's actually going in solution are the actual ions. So I could then ask how many ions of Cl minus are in solution. Well, I'd start with my moles, use Avogadro's number, and get the 9.15 times 10 to the 22 Cl minus ions are going to be in that solution. So if I want to know number of atoms, ions, or molecules in solution, I've got to use that Avogadro's number as the last step. Majority of the time, though, I'm just going to stop at the moles. I'm just going to be dealing with moles in these solutions. Concept we need to talk about, and that we're going to talk about a lot more, is something called molarity. Molarity is a unit of concentration. It's going to be equal to the number of moles of solute divided by 1 liter of the solution. Okay, so we can calculate molarity of solutions by determining those moles in the volume. So if I have 7.25 grams of MgCl2 dissolved in 127.5 milliliters of water, I want to know what's the molarity of the MgCl2 solution. Well, first I want to get my number of moles of solute. So to do that, well, my solute's the MgCl2, so I need to convert that to moles. Take my grams, use the molar mass, convert it to moles. Alright, next I can throw those moles in the top part of my molarity equation, and then on the bottom of that I want to put my volume. Ultimately I want to get it to number of moles per 1 liter of solution to report out molarity, but I don't have 1 liter of the solution here. So I've got to take the moles I have divided by the volume I have, convert that volume then to liters, and when I do that conversion, I end up with moles of solute over 1 liter of my solution. So it's 5.97 times 10 to the negative 1 moles of MgCl2 divided by 1 liter of the MgCl2 solution. We can then report that out as just 5.97 times 10 to the negative 1 capital M. Capital M stands for molarity, MgCl2. Sometimes that capital M, you hear people call it molar. So it's a 5.97 times 10 to the negative 1 molar solution. Now, one thing I want to point out with these calculations, if you look at all these calculations, you can see I've gotten specific. I haven't just written grams, I haven't just written moles, I haven't just written milliliters. I've gotten specific to describe these units better. It's going to be vital that you do that, because when we get to more complicated problems and we have multiple solutions, if you're not keeping track of which solution is which, you're going to get lost and your units are going to look all the same. Okay, so get specific with those units. The last thing we're going to look at, we're going to combine those concepts of electrolytes, non-electrolytes with this molarity concept, and we want to be able to give relative predictions of concentrations. So, if I have KBr, I know it's a strong electrolyte, and I dissolve 0.1 moles of KBr in 1 liter of solution. Well, 0.1 divided by 1 is 0.1, so I'd expect it to be 0.1 molar KBr, but what would the concentration of K1 plus be in that solution? You've got 3 choices. 0.1 molar KBr, it's a strong electrolyte. Well, if it's a strong electrolyte, that means all of it is going to dissolve, so I'd end up with 0.1 molar K plus. So A would be the correct answer. That's with a strong electrolyte. If I look at HF, which is a weak electrolyte, dissolve the same amount in 1 liter solution, I'd end up with technically 0.1 molar HF. Because it's a weak electrolyte, though, not all of it is going to ionize, and so we're not going to form 1H plus for every HF we have. Because of that, we'd expect the concentration to be less than 0.1 molar. Why? Well, because the number of moles of that H plus is going to be smaller than the 0.1 moles of the HF. Okay, so strong electrolyte, those concentrations are going to be the same. Weak electrolyte, because it's not going to completely dissolve, we're going to end up with fewer moles than we'd expect, so it's going to be less than that concentration. All right, if we take this compound, C7H6O2, and it's a soluble non-electrolyte, if we dissolve 0.1 moles of that in 1 liter of solution, what would you expect the concentration to be? Well, the concentration would be 0.1 molar. Remember, simply because it's a non-electrolyte doesn't mean it can't dissolve. It just means it's not going to form ions in solution. So we can still have a 0.1 molar concentration of a non-electrolyte as long as it's soluble. Those are the basic concepts to get you started with dealing with solution chemistry, dealing with these things forming ions in solution, dealing with all the electrolytes, non-electrolytes. It's very important stuff conceptually to get down, as well as those calculations are going to be important, but we're going to see a lot more of those.